All right. In this third problem of this group, we shall study entropy of mixing. Entropy, which is a very important topic, entropy of mixing. The problem is as follows. I have two gases, two different gases. They are separated. And here I have two gases, A and B. I have Na moles of this gas, A, in volume VA, and B at VB. And initially, both have the same temperature and pressure. So P and T, they have the same pressure and same temperature initially. So this is the initial. Now we open the valve. Both gases are occupying the total volume, and temperature is again T, because it's the free expansion of an ideal gas, and we discussed this. Temperature does not change. That's the famous experimental result. But of course, total pressure is P, but the partial pressures are not P because the gases occupy a larger volume. They have PA final, PB final. PA initial was P. PB initial was P, but finally they are not the same, and of course they drop in pressure, but the total pressure, if you add them up, is equal to P. So the question is, what happened to the entropy? Well, for a single gas, entropy had increased. For two gases, the same thing happens. For everyone, entropy increases. So let's write the entropy initial as initial total is SA initial plus SB, let me write here, initial SB initial, and let me just take this one. NA CVA log T plus NA R log VA divided by NA plus NA S0A, entropy constants would be different, TV, plus for the B, NB, CVB log T plus NB R log VB or NB plus NB S0B TV. Now, final entropy as final total is equal to SA final plus SB final. That's equal to, well, temperature did not change, so Na CVA log T plus Na R log. Now VA changed. VA is now full V, because from VA it has expanded to the full V, okay, total V. And so it is not VA over NA, but V over NA plus NA S0A TV plus the same thing for B plus NB CVB log T plus NB R log V over NB plus NB S0 B TV. Delta S is the difference. Delta S is the difference. S final minus S initial total. Let's look at it. These terms cancel the same. Entropy constants cancel. NAR log 1 over NA, so they cancel. What remains is that NA R log V over NA plus NB R log V over NB minus NAR log VA over NA minus NBR log VB over NB. So these NA terms, NB terms will also cancel. So delta S equals NAR log V minus VA. So log V over VA plus NB R log V over VB. Since V is larger than VA and V is larger than VB, certain entropy is increased. By the way, this is the increase of entropy of the gas A. This is the increase of entropy of the gas B. Let me erase here. So what is V over VA? We can perhaps also write it in a different way. For example, PVA is equal to NA RT. PAV is equal to NA RT. Same thing with the other one. PVB is equal to NB RT. PBV, big V, is equal to NBRT. And if we add them, PA plus PB is V. PV is equal to NA plus NB RT. So if we just divide these two, V over VA is NA plus NB over NA. Same thing for the B then. V over VB is equal to NA plus NB over NB. So let me just insert that. I'm erasing this part. We don't need this anymore. We need these. Therefore, delta S is equal to NA R. And let me divide by R. This is NA log NA plus NB over NA plus NB log NA plus NB over NB. We can also write it this way. NA over NA plus NB is the concentration of A, what percent, and NB over NA plus NB is equal to XB, with of course XA plus XB is equal to 1. So this is equal to minus, and if I divide delta S divided by R NA plus NB, that's equal to minus XA log XA minus XB log XB. So it's another way of writing it. But basically it is this. This is part A. We did different gases. Different gases. Okay, let this one stay. I'm raising it. So if we mix these two gases, entropy increases. Now the important question is, what if the gases are the same? Does the entropy increase again? Now, initial, so let me write here different gases. Initial entropies do not change. Instead of A and B, now A and B are not different gases, the same, so we call it N1 and N2. The original replace Na by N1 and B by N2. Initial entropy is the same. But the final entropy, you have to be careful in writing. S final total, or S total final equals, I look at here, this is now N1 plus N2, N1 plus N2. I'm not writing CV1, CP, because there is only one CV. CV log T plus N1 plus N2 R, now this is important, log V over N1 plus N2 plus N1 plus N2 S0 TV. So when we subtract from the initial, this part will go away, this part will go away, and we have to use this one. Remember, in the previous case, we had N1 log V over N1, and we had log V over N2 for the final entropy. But we don't have V over N1 and V over N2 anymore. We have V over N1 plus N2. So please compare these versus this one. Okay. So delta S is equal to this cancelled, that cancelled. So, and I divide by R. So N1 plus N2 log V over N1 plus N2 minus N1 log V1 over N1 minus N2 log V2 over N2. Now let's look at these. Initially, P V1 is equal to N1 RT. P V2 is equal to N2 RT. This is when the valve is still there. Now we have opened. P V is equal to N1 plus N2 RT. Therefore, V1 over N1 V1 over N1 is equal to V2 over N2. That's equal to V over N1 plus N2. So these ratios are all the same. So let's call it X. So this is, and so these are all the same ratios. So this is N1 plus N2 minus N1 minus N2 times log X, and the result is 0. So if you take out the valve for the same gas, entropy does not increase. So entropy increases if the gases are different gases, they mix, but if it's the same gas, entropy does not increase. In fact, this is a satisfying result. What if the gases are the same? Let's write the result here. Delta S total is equal to 0. If it's the same gas, entropy does not change, remains the same. Let's look at here. Let's take a gas, ideal gas, so PV is equal to nRT. Suppose I divide it into K cells of volume V over K, and so I make partitions. So each one is Vk with Nk particles. You see, if the entropy had increased, then we could imagine a gas in volume V such that there were K partitions, K cells, and then the valves are opened. It is mixing. That means you can make the entropy as large as you want, as arbitrarily as you want, if it had increased. So it's satisfying that it does not increase. It's I don't have to look at the past of this gas, how many partitions had been lifted. Because if there was a partition like here and it was lifted off for the same gas, the entropy would not change. So entropy of mixing for different gases, yes, we have an increase in entropy. And for the same gas, no, entropy does not change.